it is a section 14.4, tangent planes and linear approximations. In Calculus 1, you learned how to get tangent lines using the derivative as the slope. Look at the figure left side. For the curve y equals f of x, this is the tangent line, and this is the point slope form of the tangent line. Here f prime a is the slope at the point. We may use the tangent line to approximate the function values around the point, because the curve resembles the tangent line. We'll do the same for functions of two variables. Z equals f of xy will make a surface. Now, rather than tangent line, we'll try to construct a tangent plane at a point and try to use it to approximate the function values. Okay, first we'll try to get the tangent plane for z equals f of xy at a point. Any tangent plane passing through the point has the equation of the form, x, y, z are chosen from the tangent plane, arbitrary point, and x0, y0, z0 is the point, and capital A, B, C is the normal vector. So point N, normal vector, so we can get this one. In fact, and in vector notation, normal vector dot, the dot product, and x minus x0, the given point, equals 0. In detail, we can write in this way. Now, we may assume C is non-zero. C, if we see 0, then at the point, the surface is vertical. So it has a little bit of problem, and so that we assume C is non-zero. Then we can move this to the other side and divide by C, and introducing small a, small b, then this equation can be written this way. Now we have to decide A and B. Look at, so that, for example, for the plane, it can be written in this form. Now we have to decide A and B. Now we choose y equal y0. In this case, it's B. And then that means along x direction, we have that one. So this is basically the tangent line in x direction. So once y equal y0, then this portion is at the tangent line in x direction, so that like in this one, this must be x directional derivative. So we can say that here, okay, once we choose y equal y0, then this disappears. Then we have that one. Now this is x directional tangent line, so the A must be x directional slope, which is now the partial derivative f sub x. Similarly, by taking x is x0, we have this one equals that one. That is now y directional tangent line. So B must be y directional slope, which is the same as f sub y. So B is f sub y at the point. Okay, here we can summarize the argument. Suppose that f of xy has continuous partial derivatives. An equation of the tangent plane, and we say sometimes linear approximation, to the surface z equals f of xy at the point is given in this way: z minus z0, f sub x, the slope, x directional slope, x minus x0, and y directional slope, f sub y, y minus y0. That's an equation of the tangent plane. Let's try to solve this problem. Find an equation for the tangent plane to the elliptic paraboloid given here at 1, 1, 3. So that is x0, y0, z0. Of course here, once x is 1, y equal 1, then z must be 3, right? Okay. Now we'll follow exactly this formula. Already we know z0. This is known. Now we have to find f sub x, f sub y. Okay. Here, f sub x, this is f of xy. So x derivative is 4x. F sub y, y derivative is 2y. Now, at 1, 1, x is 1, y is 1, the value will be 4, and now there is 2. F sub x at the point is 4, f sub y at the point is 2, right? So using the formula, z minus, okay, z0 is 3, equal, now f sub x at the point is 4, now x minus x0, which is 1, and plus 2, and now y minus, okay, there's 2 here, and y minus y0, okay? So you can simplify. Yeah, you can move this one to the other side, and you can simplify to get that equation. Okay. Now, here we define linear approximation or linearization of the function f at a, b. That is given in this way. Yeah, f of xy is approximated by the tangent plane, and then we try to write down in this way L of xy. So it's a linear approximation. We are using L here, and that is same as f at AB, and this one, okay, that is given in this way. Here we move this one to the other side, then z equals, okay, z equal and z0 plus this one and that one. Now for this z, okay, that one, in fact we choose this one on the tangent plane, so that by using L of xy, because this portion is a function of xy, we try to use that portion as the notation here, L of xy. So that is defined in this way. Okay, so this portion is called the linear approximation, linearization. Okay, give the linear approximation of f of xy at 1, 0, and use this to approximate the value. Then once you are using this linear approximation, that means we are trying to approximate the function value using the tangent plane. So the value is the value on the tangent plane. Okay. Okay, now here, first of all, we have to find f at AB. AB is given 1, 0, so that f here 1, 0. Okay, is x is 1, y equals 0, so that must be 1. We decided that one. That is A, and that is B, right? Now f sub x derivative, the x is here, x is here. So by using the product rule, we can get e to the xy plus now xy e to the xy. Now f sub y derivative, then y appears here only once. And if you make y derivative, then x will come out, so that is x squared e to the xy. Now we are using here the point, and that is 1 and 0. X is 1, y equals 0. So that is e to the 0, y equals 0, so that will be 0. So that is 1. Now again, using the same point, x is 1, y equals 0. Okay, that is again 1. So we can conclude here L of xy is the same as that value 1 plus the slope is 1 and x minus a, so there's x minus 1 plus slope is 1 and y minus b, which is 0. Okay, so that is now x plus y minus 1 plus 1, so that we reach x plus y. That is the linear approximation. Okay, now we would approximate the function value by using this one, so that L 1.1 and minus 0.1, then just simply addition of them, 1.1 and plus and minus 0.1, which is same as just 1. Okay, so approximate the value is 1. But if you try to measure this real value at 1.1 and minus 0.1, then you will see this is 0.9854, like that. So here, around 1, 0, this tangent plane approximation or linear approximation is approximating the function value quite well. Okay, now we'll go to differentiability. So far, in fact, in the last section, you learned partial derivatives. These partial derivatives are just directional derivatives along coordinated directions. The question is, these derivatives can be obtained for every arbitrary directions. That's the question. The differentiability is related with the question, and will define the differentiability in this definition. Okay. In order to do that, let's begin with a recall. For functions of one variable, y equals f of x, we said it is differentiable at the point A if this limit for the quotient, the limit exists as delta x approaches 0. And that is the definition of the derivative. You learned this one in the beginning of the calculus. Now we try to use the notation for the limit here, f prime of a. So if f is differentiable at a, then now eliminate this limit, then this quotient will be around the value f prime at a, and the difference will be epsilon. And we use the notation and epsilon to indicate they are not the same, but they are really near each other. So along with the epsilon, we write in this way rather than using this limit. We multiply delta x, then this left-hand side, this side is same as this one. And we define this portion change in y direction. Now, in this equation, epsilon is approaching 0 as delta x approaches 0. That's the meaning. So rather than using this definition for differentiability for the function of one variable, we may try to use this one here as delta x approaches 0, epsilon approaches 0, then we say it is differentiable. Now, for z equal f of xy, and now xy changes from ab to and a plus delta x, b plus delta y, then the corresponding change of z is given in this way. The delta z is given here. Here we have the definition for differentiability for functions of two variables. For the function, it is differentiable at the point if delta z, change of z, is given in this way. Here the condition is epsilon 1, epsilon 2 approaches 0 as delta x and delta y approaches 0. So exactly the same as this one we define in this way. Of course, here such number exists, and that is a number, and in this definition f prime a exists such that here when delta x approaches 0, epsilon approaches 0, the same way, these two numbers exist as n, now epsilon 2 approaches 0 simultaneously as delta x, delta y approaches 0. Okay, that's the definition. Once you try to use this definition to check if the function is differentiable, then it's very hard. Now, we have a theorem. If f sub x, f sub y, the partial derivatives exist near the point AB, and they are continuous, then z equals f of xy is differentiable at AB. So to check if the given function is differentiable, you have to check if partial derivatives exist and continuous. Then that's it. The above theorem implies that if partial derivatives f are continuous, then the slope of f exists for all directions. So eventually, differentiability means that rather than only the coordinate directional slope, can we find slopes in arbitrary directions? That's the question. And along with the theorem, the answer is yes, when the partial derivatives exist and they are continuous. Okay? Let's try to solve this problem. F of xy equals y plus sine x over y. Explain why the function is differentiable at the point 0 and 3. Okay, now at 0, 3, nothing is wrong. The function is continuous, and also we can get partial derivatives. Let's try to get it. F sub x, x derivative, okay, that will be 0, and that is, along with this block, we make a derivative, which is cosine x over y, and x derivative, which is 1 over y. Now, f sub y, y derivative, that will become 1, and again, along with this block, we make a derivative, which is cosine x over y, and for x over y, y derivative will be okay, x and minus y squared on the bottom. Now, around the point 0, 3, this is continuous, and y is on the bottom, and is far away. 3 is far away from 0, so that these two are continuous. They exist and continuous, so that the function is differentiable at 0, 3. Okay. Okay, differentials. We have a recall for y equal f of x, a function of one variable. Dx is the differentiable x, is an independent variable. Then differentiable y is defined as here, dy equals f prime x and dx. Like y equal f of x, then dy over dx equal f prime x. And this derivative can be seen as a quotient. In fact, it's not a quotient. But if you look at this one as quotient, then now dy is the same as f prime x dx. Now, you learned this one from calculus 1. And here you have to be careful for that one. Dy is representing the change in height of the tangent line. So that one is the change along the tangent line. But delta y, if you're using delta y notation, then that is real change along the curve. But dy is changing along the tangent line. Now, similarly for the function of two variables, we'll define differentials. We define differentials dx and dy. Of course, that is independent variable. Now, we define the differential dz as the dependent variable in this way. Dz is f sub x dx plus f sub y dy. Then we call sometimes this one the total differential. Of course, this one is change along the change on the tangent plane, not change of the real function values. You have to be careful. dz is indicating the change on the tangent plane. Okay, so we define this differential in this way. Okay, let's now dx is a change in x direction, dy is a change in y direction. So let's go back to tangent plane. And so here, for this one, this is change in tangent plane, and f sub x and change in x direction, and f sub y change in y direction. So differential is basically the representing that equation. Okay, don't be confused. DC must be change on the tangent plane. Okay, let's try to solve this problem. Z equal f of xy, x squared plus 3xy minus y squared. Find the differential, total differential DC. Okay, let's do that. Part A, DC equals f sub x and dx plus f sub y and dy. Now, what is f sub x? X derivative of that one is 2x, and x derivative plus 3y, and it'll become 0. Now, f sub y, y derivative, then there's a 3x from here, and minus 2y. So we use these two to get DC, the total differential. F sub x is 2x plus 3y, and dx. Now, plus f sub y is 3x minus 2y, and dy. Okay, that's it for part A. If xy changes from 2, 3, so that will be x and y, to 2.1, 2.9. So the change will be delta x, and this change will be delta y. And compare the values of DC, delta c, and DC. Okay, part B. Let's try to find the DC for this one. Now, x is 2, y is 3. How about dx? Change in x is from here to there, which means there's 0.1. And change in y, dy, from 3 to 2.9 minus 0.1, right? Okay, we use these values. That is 2x, 4 plus 9, 4 plus 9, and dx is 0.1 plus 3x, that's 6 minus x, okay, dy is minus 0.1, so that'll be 0, and this is 13, so 1.3. DC is 1.3. Now, if you want to get delta c, real change on the surface, that's same as f, the last point, is 2.1 and 2.9 minus f at beginning point 2 and 3. Okay, this is a bit complicated, so that we'll try to use early computed value. That is now 1.27. So along the tangent plane, it is well approximating 1.3, and real value, real change is 1.27. Okay. Okay. Use differentials to estimate the amount of metal in a closed cylindrical can that is 10 centimeter high and 4 centimeter in diameter. If the metal in the top and bottom is 0.1 centimeter thick, and the metal in the side is 0.05 centimeter thick. And let's try to visualize the can. It's a cylindrical can. Okay, it's given. Now, height is 10 from here to there. That is 10 centimeter. And 4 centimeter in diameter, so that this R is now 2. And the can is made along with bottom and top 0.1, 0.1 thick, 0.1, and side is now 0.05. Okay, thickness. Okay, here, if we try to find the approximate amount of metal, then we may start with volume equation of the volume. Of course, here the amount of metal is, in a sense, volume change. So once we start with the volume V, then dV is the change in volume along, in a sense, tangent plane. So it is an approximation. Now pi times r squared times c is the volume. We can easily see that. So this is a total volume. Now that is a volume change. So you may think in this way, and out of this whole volume, just the can is just a volume change. So by using dV, we can get the approximate amount of metal. Right? Okay. So dV is VR derivative dr plus VZ derivative dz. R derivative of V is 2 pi r z, just R derivative and dr, and Z derivative is pi r squared and dz. And we have to find these quantities. Now dr, of course, we already know that R is 2 and Z is, that 10 is Z, the height, and dr is 0.05, the thickness inside, and dz is the thickness, that is 0.1 and another one, so that twice of 0.1, which is 0.2. Use these quantities, use the data, we can get dV. Okay, dV equals 2 pi. R is 2, and Z is 10, and dr is now 0.05, and plus pi r squared, which is 4. Now dz is 0.2. Right? Okay. Now there's 1 over 20. Okay, cancel out. So that portion is 2 pi plus that is 0.8 pi. So it is 2.8 pi. So that's the final answer. Okay. And okay, the numeric value of 2.8 pi is this one, 8.79. And now for real value, once we start with here in R is 2 and 10, and try to make the thickness and the outer volume and subtract the inner volume, and we can get real volume, which is now here 9 point something. But anyway, this one is approximating well the real change. Okay. Okay, that's the end of the section. Thank you.